Pluto, a distant and enigmatic object in our solar system, was once considered a full-fledged planet. For years, it held a prominent place as a vital part of our planetary family. However, recent revelations by esteemed astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited curiosity about Pluto. These scientists have put forth a surprising theory that Pluto might be headed toward a catastrophic collision with Neptune. This raises intriguing questions. How could such an extraordinary event occur? What would the consequences of such a collision be? Is this a rare anomaly in the cosmos? Or could there be more to this potential event than we currently understand? Let us explore the possible outcomes of a hypothetical Pluto-Neptune collision. Once classified as a planet, Pluto was later redefined as a dwarf planet, yet it still sparks immense interest among astronomers and researchers who continue to study its mysterious nature. According to recent studies, Pluto's orbit brings it dangerously close to Neptune's, and experts like Tyson and Kaku have warned that a potential clash between the two celestial bodies could even pose risks to Earth. But what exactly would it take for such a disaster to occur? Pluto's orbit around the Sun is remarkably different from that of the other planets. It takes an incredible 248 years for Pluto to complete one full revolution around the Sun, meaning that since its discovery in 1930, it has not yet completed a single orbit. But what's even more fascinating about Pluto's orbit is its highly irregular shape, unlike the nearly circular orbits of most major planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making its motion more erratic than that of the other planets. This orbital peculiarity makes Pluto's behavior unpredictable, adding complexity to our understanding of its motion. Another particularly intriguing aspect of Pluto's orbit is how it interacts with Neptune's. During certain parts of its orbit, Pluto crosses into Neptune's orbital path, which is unexpected based on their presumed positions within the solar system. This raises an obvious question. If Pluto crosses into Neptune's orbit, why hasn't a collision occurred? The answer lies in the gravitational effects of other celestial bodies within the solar system. When astronomers first discovered Pluto, they were puzzled, led by the strange shape of its orbit. Unlike the relatively flat orbits of most planets, Pluto's orbit stood out due to its steep inclination and highly irregular path. To explain this odd behavior, scientists turned to a concept called the three-body problem in celestial mechanics, which attempts to understand the interactions and movements of three celestial bodies: the Sun, Neptune, and Pluto, each exerting gravitational influence on the others. This concept is similar to predicting the future positions of these objects based on their current locations and the forces acting on them. When applied to Pluto's orbit, the three-body problem helps explain how the Sun, Neptune, and Pluto interact with each other. Certain phenomena, like libration, oscillatory libration, and VSK wobbling, play crucial roles in resolving this mystery. These concepts suggest that Pluto's orbital stability may be linked to libration, a phenomenon where the relative positioning of Pluto and Neptune is offset by about 90 degrees. When Pluto crosses Neptune's orbit, this offset ensures that their paths don't align, which prevents a collision from happening. Essentially, libration helps keep Pluto above the plane of Neptune's orbit as it nears Neptune or other large planets, protecting it from potential crashes. Another important factor keeping Pluto's orbit stable is the VSK wobbling, named after the scientists who explored it. This term describes how the gravitational force between Pluto, Neptune, and the Sun influences the movement of these objects, ensuring that Pluto's orbit remains steady despite its unusual shape. This complex gravitational interaction is vital for maintaining the stability of Pluto's orbit over extended periods. Even though its path appears chaotic, the three-body problem is critical for understanding how celestial bodies interact. It allows scientists to predict the behavior of distant stars, planets, and other celestial objects. mathematical simulations from the late 1980s revealed that even though Pluto's orbit is highly irregular, its trajectory remains relatively stable, with only slight deviations from its original path. These steady characteristics of Pluto's orbit have remained consistent, enabling astronomers to refine their models of its movement. Recent computer simulations have also provided insight into how massive planets like Neptune, Jupiter, and Saturn affect Pluto's orbit. One unique feature of Neptune's relationship with Pluto is their orbital resonance, which follows a 2-to-3 ratio. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit, preventing a collision. However, Neptune's gravitational influence is not the only factor at play. Jupiter's immense gravitational field also plays a critical role in stabilizing Pluto's orbit. Additionally, Saturn's gravity helps maintain stability in the outer regions of the solar system. Studies suggest that Jupiter's powerful gravitational field is enough to keep Pluto's orbit remains stable for billions of years, possibly ensuring that Pluto remains on its current path indefinitely. Together, Neptune, Jupiter, and Saturn work in harmony to stabilize Pluto's orbit, preventing disruptions within the solar system. Without these massive gravitational forces, the cosmos would be far more chaotic, with objects like Pluto potentially colliding with other bodies or even being ejected from their orbits, causing major upheavals throughout the universe. Understanding Pluto's orbital dynamics is crucial, particularly as concerns about a possible collision with Neptune intensify. The delicate relationship between Pluto's orbit and Neptune's provides valuable insight into how planetary systems interact. Pluto's case demonstrates that even highly erratic orbits can achieve stability through the complex gravitational interactions between celestial bodies. Studying Pluto's orbit underscores the need for ongoing observation to keep our understanding of the universe current. Exploring space continually brings us face to face with the strange and unpredictable nature of celestial objects. Pluto's orbit is a prime example of this unpredictability, showing how even the most chaotic systems can maintain a stable course due to the influence of gravitational forces. The 2-to-3 orbital resonance between Pluto and Neptune is a key aspect of this system, ensuring that even though their paths intersect, the two bodies avoid a collision. This gravitational relationship is foundational in celestial mechanics, proving that even the most irregular orbits can eventually harmonize. In addition to Neptune's gravitational impact, other massive planets such as Jupiter, Saturn, and even Uranus play crucial roles in maintaining the balance of the solar system. Jupiter's immense gravitational field serves as a protective force, helping keep smaller objects like Pluto on track. Some scientists believe that Jupiter's gravity may have even prevented Pluto from being ejected from the solar system, further highlighting the importance of understanding gravitational dynamics within our cosmic neighborhood. While Pluto's orbit appears stable for now, it's essential to acknowledge that changes could take place in the distant future. Astrophysicists like Neil deGrasse Tyson continue to explore the cosmos, uncovering deeper insights into the forces that govern the movement of celestial bodies. Although the chance of a Pluto-Neptune collision seems remote, the mere possibility serves as a reminder of the ever-changing nature of the universe. It reinforces the importance of continued exploration to expand our understanding of the forces shaping our solar system. As research into Pluto's orbit and its interactions with other celestial bodies progresses, it remains essential to advance our knowledge of the broader universe. Pluto's situation offers a compelling case study in the complexities of orbital resonance, where the movements of celestial bodies are intricately intertwined. The 2-to-3 orbital resonance between Pluto and Neptune ensures that despite their intersecting orbits, the two bodies never collide. This gravitational balance has preserved Pluto's orbit for billions of years, illustrating how seemingly chaotic systems can achieve stable and predictable outcomes. The significance of this resonance cannot be overstated. It represents a fundamental principle of celestial mechanics, proving that even complex orbital behaviors can eventually align due to the gravitational forces at play. Understanding orbital resonance extends beyond just Pluto and Neptune. It sheds light on the broader dynamics of the solar system. The interactions between planets, dwarf planets, and other celestial bodies are essential in maintaining the stability of our solar system. Jupiter's critical role in this process cannot be overlooked. Its immense gravitational influence acts as a safeguard, helping smaller bodies, like Pluto, remain on their established trajectories. Jupiter's gravity extends beyond Pluto, impacting the orbits of asteroids, comets, and other small objects in the outer solar system. This interconnectedness highlights the role of gravitational forces in preserving equilibrium within the solar system. Some researchers even suggest that Jupiter's gravitational force might have helped secure Pluto's place in its current orbit, preventing it from being ejected from the solar system. This further emphasizes the idea that each planet plays a specific role in maintaining the overall structure of the solar system. Studying Pluto's orbit and its gravitational interactions with other planets offers insights into the dynamic nature of space. While mathematical models and simulations provide valuable understanding of celestial mechanics, they also reveal the uncertainty of predicting long-term movements. Small changes in initial conditions or minor variations in gravitational forces can result in drastically different outcomes over time, highlighting the complexity and unpredictability of space. This uncertainty reinforces the need for continuous observation and analysis. Studying systems like Pluto offers vital lessons about the forces governing the motion of celestial bodies. Pluto's orbital stability, despite its irregularities, underscores the power of gravitational forces and the self-regulating nature of orbital mechanics. As space exploration continues to advance, it becomes increasingly clear that understanding the delicate interplay of these forces is crucial for uncovering the broader dynamics that govern both our solar system and the universe at large. As research into Pluto's orbit and its interactions with other celestial bodies progresses, it provides valuable insights into the fundamental principles governing the solar system. The fact that Pluto has maintained its orbit for billions of years, despite its seemingly erratic path, highlights the extraordinary nature of gravitational interactions. These interactions preserve cosmic order, even when objects like Pluto appear to follow unpredictable trajectories. Maintaining this balance is critical in preventing